There's a secret shape hidden all around us, in plain sight. It's this incredibly graceful, powerful curve that pops up in nature, in sports, even in our most amazing architecture. So what's the deal? What's the hidden mathematical rule that governs this one beautiful shape? Well, today, we're going to pull back the curtain and crack that very code together. I mean, think about it. You see it in the perfect arc of a basketball just before it swishes through the net. It's like a moment of pure physics, just frozen in time. You can trace that same shape in the streams of water that dance in a fountain. Every single droplet follows that exact same elegant path.
And you can literally see its strength holding up these massive structures, right? Like the sweeping cables of a suspension bridge. This universal curve, it's just everywhere.
So this shape actually has a name. It's the parabola. And today, we're going to peel back the curtain and really look at the mathematical blueprint that designs every single one of them. And that blueprint, that secret code we're talking about, it's an algebraic formula, and it's known as the quadratic function. And believe it or not, it holds the instructions for drawing every single parabola in the universe. And here it is. F of x equals ax squared plus bx plus c. Now, it might look kind of simple, but don't let that fool you. Absolutely everything about a parabola, its shape, its direction, where it sits on a graph is controlled by just these three values, a, b, and c. They are literally the keys to the entire code. Okay, so let's do this. Let's decode this function piece by piece. We're going to start with the most influential character in our code, that first coefficient, a. So the a value, it basically sets the entire mood of the parabola. If a is a positive number, the parabola opens upwards, kind of like a smile. And that means it has a single lowest point, what we call a minimum. But if a is negative, it flips and opens downwards, like a frown, giving it a single highest point or a maximum. Simple as that. But wait, there's more. A also controls the parabola's width, and this is where it gets a little weird, a little counterintuitive. A bigger number for a doesn't make the curve bigger, it actually squeezes it, making it really narrow and steep. A smaller a, something closer to 0, stretches the parabola out, making it much, much wider.
All right, next up is b. Now, b is a little more subtle. It works with a to kind of slide the whole parabola left or right. But here's an easy way to think about it. The b value tells you about the slope of the curve at the exact moment it crosses that main vertical axis. So if b is positive, the curve is rising at that point. If b is negative, it's falling.
And finally, we get to c. And honestly, c is the easiest of the three. The c value is simply the y-intercept. That's it. It's a fixed anchor point. It tells us the exact spot on the vertical axis where our parabola has to pass through. It gives us a precise starting coordinate, the point 0, c. Okay, so now we know how to shape and place the parabola. Let's learn how to actually map it out. We're going to find its most important landmarks, where it hits the ground and its absolute highest or lowest point. First up, we have the roots, which are sometimes called the zeros. These are simply the points where the parabola crosses the horizontal x-axis. In the real world, these are often the solutions to our problem, the x values that make the whole function equal to 0. But hang on, how do we even know if a parabola has any roots at all? Well, before we do any of the heavy lifting, there's this really cool shortcut called the discriminant. By calculating this one value, we use the Greek letter delta for it, we can predict exactly how many times our parabola is going to meet that x-axis. It really just comes down to three possibilities. If delta is positive, we get two different roots. The parabola slices right through the x-axis in two places. If delta is exactly 0, we just get one root. The parabola comes down and just kisses the axis at a single point. And if delta is negative, well, we get no real roots at all. The parabola completely misses the axis, just floating above or below it. So when the roots do exist, this is our ultimate decoding tool, the quadratic formula. Now, I know it might look a little intimidating, but just think of it like a recipe. You just plug in your numbers for a, b, and that discriminant we just talked about, and boom, the formula spits out the exact x-coordinates where the parabola crosses the axis. Okay, the last landmark, and this is the big one, the vertex. This is the official turning point of the parabola. It's either the absolute bottom of the valley or the absolute peak of the mountain. And just like the roots, yep, it's got its own formula, giving us the exact x and y coordinate for this super critical point.
All right, we have decoded the function. We have all the tools we need. So now it is time to put them to the test with a real-world physics problem.
So here's our mission. The path of a projectile is described by this quadratic function, and the question is simple. What's its maximum height? So what is this question really asking? It's asking for the y-coordinate of the vertex.
Let's break down the function. First thing, notice that a is -20. Right away, that tells us the parabola opens downwards, which confirms that the vertex is a maximum point. It's the peak of the flight. So all we have to do now is use our vertex formula to find its exact height.
So we just take our values for A, B, and C right from the projectile's equation. First, we calculate the discriminant, then we plug everything into that y-coordinate part of the vertex formula, and the code reveals its secret. The maximum height that projectile is going to reach is 405 meters. We got all of that from one simple equation.
But, there's actually a little more to the story here. If we calculate the roots of the same function, we find out they're at 0 and 9. What does that tell us? It tells us when the flight starts, at time 0, and when it ends, when the projectile hits the ground 9 seconds later. The parabola gave us the entire story of its journey.
So, there you have it. We've cracked the code. From a pretty simple-looking formula, we can predict, we can map, and we can understand this fundamental shape of the universe. So the only question left is, now that you know what to look for, where are you going to see the next one?